So I was saying good morning, good afternoon, and good evening even to everyone. I'm Maxime Maurice, a postdoc at Rice University, and along with Daman, who you'll meet in a moment, as well as the whole Clever Planet team, that's our great pleasure to welcome you to this first seminar of the Clever Planet Fall 2021 seminar series. This seminar will take place every 2 Tuesdays at noon Houston time. And they are organized by the Clever Planet, which is an interdisciplinary multi-institutional research initiative to unravel the conditions of planetary habitability in the solar system, as well as in exoplanetary systems. Its lead institution is Rice University, and we are supported by NASA and are one of the team of the Nexus Exoplanetary System Science Research Coordination Network under astrobiology. In the seminar series, we will cover broad topics of planetary habitability, which utilize expertise in astrophysics, geochemistry, petrology, geodynamics, geophysics, and related disciplines. And before I give the floor to Daman, who will introduce today's speaker, we'd like to proceed to a land acknowledgement. And while we are interested in the habitability of other planets, we are no less interested in being able to inhabit our own world peacefully as human. And failing to acknowledge that the land on which our research is done is the traditional land of native people is a form of perpetuation of the colonization they've been victim of. Therefore, it seems very important to us to speak about that. Although this seminar is held online, it is organized by Rice University, which is located in Houston, Texas, between the traditional territories of various native people. So the Karankawa, which went extinct by the middle of the 19th century, direct victim of the colonization, but also the Coahuiltecans, whose territory goes from northeast Mexico up to north of Houston, and who are today represented by the Tapilam Coahuiltecan Nation, the Ishak, also known as Atacapa, whose traditional territory is along the coast of the Gulf of Mexico, and who are today represented by the Atacapa Ishak Nation, and the Sana, who have been related through their language to the Tonkawa, who are now principally settled in Oklahoma. I will put a few links towards internet resources on these native people, and in the chat, and I strongly encourage everyone, in particular our fellow Houstonians, to visit them. And now, without further ado, I'll let the floor to Daman, who will introduce our speaker for today.
Thanks, Maxime. Hi everyone. My name is Daman, and it's my great pleasure to introduce today's speaker, Max Collinet. So Max did his bachelor's at University of Liège in Belgium. He did his master's at University of Clermont-Ferrand in France on analysis of Ergodites, and he did a few experiments related to Mars. He did his PhD at MIT, working with Tim Grove, and this was basically it was based on experiments on simulating melting in planetesimals as well as Martian mantle. Currently, Max is a postdoc at DLR in Berlin, and he's working on modeling of melting in the Martian mantle. And he's also collaborating with National History Museum of Berlin to do some Achondrite analysis. But before I give this stage to Max, I just want to say that this talk is going to be 40-45 minutes, followed by question and answer round of 10 to 15 minutes. And questions can be either put on the chat window, or they can be asked by raising your hands at the end of the talk. So Max, you may start.
Great. So I'm going to share my screen. Okay. Let's go. Dun, dun, dun. Oops, sorry. Let's go full screen. And I'll take a pointer just so you can see what I'm showing. Okay, well, thank you very much for the invitation and for the nice introduction. So the work I will present today is really connected to my PhD work I did at MIT with Tim Grove. There are a few more ideas and some updates, but it's mostly my PhD work. And so the premise of this work is that we can study meteorites and asteroids to learn something about the processes that occurred in planetesimals, so the building blocks of planets. And so those planetesimals formed at very different heliocentric distances, but were then mixed together during accretion to form the terrestrial planets, and some were preserved in the asteroid belt. So we can really hopefully study those in the meteorite record and learn something about how the planets reach their current composition. So of course, it's we have been collecting meteorites for a long time, and Achondrites in particular have been recognized for a long time as coming from partially differentiated parent bodies. So just for fun here, I'm showing 3 historical work that attest of that. So here is a sketch by Boas, where he places the Achondrites in the crust of planet or large parent body that was destroyed. And so the iron meteorites would be at the core. So this idea that we had differentiated planetesimals, so planetary embryo was already present. Then Rose also made some analogies between eucrites and terrestrial basalts and recognized that eucrites were volcanic in origin. Dobré already did experiments in those years and made some interesting comparisons between, again, igneous terrestrial rocks and some meteorites. So it's really not a new idea. But of course, now we have a larger meteorite record and different tools to use. So the meteorites that I'll be talking about are believed to come from the planetesimals that were only partially differentiated, so that melted maybe between 0 and 30%, but not enough to form magma oceans. And so those meteorites can be grouped in 2 main families. One is the trachy-andesitic Achondrites that would represent the partial melts, and the primitive Achondrites would represent the residues left behind in the interior of those planetesimals. And so we'll talk about them first. Here are the main groups of primitive Achondrites. There are ultramafic rocks that are made of olivine and pyroxene with some plagioclase, but not in all of them, only in some brachinites and acapulcoites. So most of those rocks are also depleted in incompatible lithified elements, so which suggests that they lost a silicate melt and that there are really melting residues. On the other hand, the trachy-andesite Achondrites are quite different. They are made of a lot of plagioclase that is sodium rich. So anortite 14 means anortite poor, and albite rich, so sodium rich as well. So those rocks, even though they show the same lithology with 50 to 75% of sodium rich plagioclase, they have very different oxygen isotopes. So it's not so much a group, but yeah, in the sense that they share a common origin, but maybe just a common process. So this is the first one that was discovered, GRA 06128, and it could be linked to brachinites. Then we have 2 stones that have the same oxygen isotopes as zeolites. And then this one here is similar to L-chondrites in terms of oxygen isotopes. And then since I finished my PhD, so this new sample was discovered. It's the biggest so far. It's very interesting, and we'll talk about it a little bit later. But let's take a quick look at the chemical composition of all of those samples. So in a total alkali versus silica diagrams that plot close to the trachy-andesite joint, and the concentration in sodium and alkalis and aluminum is really controlled simply by how much of this sodium-rich plagioclase is present in the rocks. So I'll come back to this later, but yeah, let me give you the outline of the presentation and the questions we'll address. So the first one is, can we identify the initial composition of the parent bodies of the trachy-andesite Achondrites, and how does it compare to the initial composition of the primitive achondrites, so before they started to melt. Is there anything in common between those groups? And what are the implications for the distribution of alkalis, so moderately volatile elements in the early solar system? I won't be talking directly about more highly volatile elements, such as hydrogen and sulfur, but we can speculate a bit more during the discussion. So that's the first part of the talk. And the second part of the talk will be more focused on what is the type of melting process that occurred in those point bodies. Is it more like batch melting, keeping the melt in the mantle during melting, or is it fractional? We remove the melt progressively. Then I'll talk about uralites in more detail. So here are the type of experiments that we've done. We first synthesized different chondritic compositions listed here. And so note that they don't have water or sulfides, but we then put them in graphite capsules in a molybdenum hafnium carbide alloy that was then filled with CO. So the CO buffer sets the FO2, and then the experiments were done at pressure and temperature relevant for the interior of planetesimals. So we put the pressure vessel in a furnace and leave it there for a few days, take it out. So it's glowing, but we try to heat it with a wrench so that the capsule really drops into the water-cooled zone and we quench the melt. So the major contribution is that we were, for the first time, able to preserve the alkalis during kind of low pressure experiments using this device. In previous experiments in 1 atmosphere furnace, alkalis was sometimes lost. So here are 2 such experiments after the quench. This for the Achondrite composition at lower temperature. So we already have glass at 1080 Celsius degree, melting started, and the melt is in equilibrium with 2-peroxene, augite, OPX, plagioclase, and olivine. Then at higher temperature, the plagioclase disappears. We have, of course, more liquid. Melting progresses, and OPX and augite is replaced by pigeonite. Before I continue with the results, I just wanted to say a few more words about how we selected the chondritic compositions. So the main difference between those different chondrites is the enrichment, the relative enrichment in moderately volatile elements, so alkalis relative to calcium, so refractory elements. And we express this as the NAK number, the sum of alkalis divided by alkalis plus calcium. So CI, H, and LL chondrites have the same NAK number, the same alkali concentrations as the sun's photosphere, and CMCV chondrites have a lower bulk NAK number, so are depleted in alkalis and rich in calcium. What is interesting is that this parameter, the bulk NAK number, correlates directly with the plagioclase content in the subsidized experiments and equilibrated chondrites, so before melting starts. And that's because those elements are the same ones that compete for the M site here in the plagioclase solid solution in the crystal structure. So when we have a low bulk NAK number, high anotite content, and so on. And so I'll come back to this. It will become important later. So let's compare the composition of those melts that we produce in the experiments. First, looking at the melts produced from chondrites that are rich in alkalis, here in black, blue, and green. So on the same 2 figures that I was using in the introduction. So overall, the composition of the melts is very close to the trachy-andesite achondrites. And maybe what is striking is that the alkalis and aluminum concentrations really align in the same fashion and seem to be kind of controlled by how much of a sodium-rich plagioclase component we have in the melt. So that's not the case. This comparison is not as good for the melts produced from CV and CM chondrites. they are simply too poor in alkalis to be able to produce trachy-andesite achondrites upon melting. So that's kind of the first conclusion, is that the trachy-andesite achondrites are derived from the partial melts of chondritic planetimals that were not depleted in alkalis relative to the sun's photosphere, so like Ci, H, and Ll chondrites. And so here on the right, I'm showing those different samples, the trachy-andesite achondrites, in terms of their oxygen isotopes and how that compares to the major group of primitive achondrites, so uralites, acapulcoids, brachinites. And so you see that maybe they share a similar region of this diagram. And so maybe that could suggest that the initial composition of primitive achondrites was also rich in alkalis. But in this diagram, we also have this rock here that is poor in alkali. So this type, it's like also a silica-rich achondrite that is poor in alkali. So it's not sufficient to just compare the isotope, and we would like to constrain the initial composition of primitive achondrites directly by looking at primitive achondrites. So for brachinites, we can do that, and because we have some samples that are fairly primitive, meaning that they did not melt so much, and that's the case of brachina that contains plagioclase ornithite 20. So that is characteristic of a chondritic material that is alkali rich. So we can say, okay, brachinites had also a high NAK number. Same for acapulcoid slodronites, because essentially they contain chondrites in the same group, which has an NAK number of 50, same as the sun's photosphere, and also a sodium-rich plagioclase. For uralites, it's not as simple because we don't have primitive samples. So how do we do it? Well, we have one thing going for us, is that the uralite plant body is like a quenched mantle. So it was destroyed, and because of that, it cooled very fast, and we preserved high temperature phase assemblage in this mantle, so we can compare it one-to-one with the experiments that we also quench, and to learn more about the petrogenesis of uralites. So that's what we'll do. And here I'm showing a phase diagram of the experiments with the oxygen fugacity as the y-axis and the temperature as the x-axis for the H chondrite, so with a high NAK number. And so you can see exactly which phases are present at which conditions when it's filled. But we're not so much interested in the detail. We just want to notice that at some temperature, at some increasing temperature, plagioclase disappears before pigeonite, so that we have an interval where we have a phase assemblage that is exactly like uralite. So we can produce uralite with olivine and pigeonite and metal by melting an H chondrite in this gray field. So that works. That also works with an LL chondrite, so also an ordinary chondrite. And that also works with a CI chondrite. So essentially every chondrite that is rich in alkalis with a high NAK number. It's not true anymore for CM chondrite with a lower NAK number, and that's because the plagioclase, which is more calcic, melts at higher temperature. So this field that we had essentially disappears, and disappears completely for CV chondrite with a low NAK number. So now plagioclase is stable longer than pigeonite. So we never have a phase assemblage that is just made of pigeonite, olivine without plagioclase like we have in uralites. So, so on the left, there's just a summary of those different phase diagrams, and just to show you that the only chondritic compositions that would produce something like a uralite after partial melting are the ones with high concentration of alkalis, so like Ci, H, and Ll. And so that argument is kind of reinforced also by the fact that we have two trachy-andesite achondrites that are rich in alkalis and that share the same oxygen isotopes as uralites. But again, those two arguments are independent. And so together they really suggest that the uralite plant body was not depleted in majority volatile elements, and that is then would be similar to the other group of primitive achondrites. So when we put all of this together and we try to plot the relative concentration of alkalis in parent bodies before they start to melt, when it's possible, and we plot that in terms of the, so that's the classic isotopic dichotomy diagram that now has been shown to separate inner solar system material from outer solar system material in terms of the nucleosynthetic anomalies and oxygen isotope composition. So what the diagram shows is that everything in the inner solar system is rich in alkalis, high NAK number and low anorthite content. So that therefore for the few bodies for which we cannot really retrieve the initial composition so easily, we can infer that the alkali depletion is a secondary process. But yeah, that initially the inner solar system is alkali rich, and interestingly, the only primitive material that are richer in refractory elements and poorer in moderately volatile elements are all in the outer solar system. But that's a different topic. Okay, so I introduced at the beginning Erg Chech 002, that is a recent meteorite find. And it's really interesting because it's big, it's 30 kilos, and it's made of a lot of this sodium-rich plagioclase that we have seen in other meteorites before, but not in this quantity. And it's also the oldest planetary crust. So it was dated by Baha et al. 2021 at 2.2-ish million years after the condensation of CI. So it's really the oldest planetary crust, if not igneous rock, in the solar system. And yeah, it's really tells us that initially those melts were rich in alkalis. So what we can go further, and that's what Baha et al. Did. They compared our experiments to the composition of Erg Chech 002. And so they see a very good match, which suggests that, yeah, they come from an alkali-rich parent body. And they could estimate the melt fraction needed to produce such a composition to 25% of a batch melt. So 25% batch melt is yeah, it's quite a lot, I think. And how do we melt 25% while keeping such a light? So because it's andesitic, the density is fairly low. So how do we keep it in the dense residue during melting? And that could be because the viscosity of the melt is very high. So even though it's not super dense and theoretically could rise, it's very viscous, and therefore melt extraction is sluggish at the beginning of melting. So at the beginning of melting, viscosity is high, and maybe the melt cannot be extracted because of that. But as melting increases to 25%, then maybe then only the melt can be extracted, and that would be why we have Erg Chech 002 representing a 25% batch melt. And so that could be consistent with kind of a 1 million year time span between the crystallization of EC002 and the partial melting event. But of course, there's also a large error on this. One more sample that also matches the composition of our experimental melts is NWA 11575. It's a little bit richer in aluminum and lower in magnesium compared to Erg Chech. So Erg Chech is here in black, and NWA 11575 is in green. And so that is more consistent with like a 5 to 15% batch melt, so lower melt fraction. So clearly, between those two samples, the efficiency of melt extraction was different. Okay, so that being said, I want to come back to the Eurolite parent body and discuss a bit more about the detail of the melting process. Was it batch? So we keep the melt again in the residue before we extract it, or do we extract it progressively as melting progresses? So I kind of left it by saying that we can produce a mineral assemblage that looks like a Eurolite by melting chondrite with a high concentration of alkalis. And by looking at those diagrams, you can see that that's the case between 1130 and 1180 Celsius degrees. We form an olivine pigeonite assemblage. So that is true, but how unique is that result? Can we do other type of melting and also form something that looks like a Eurolite? So to answer that question, we did experiments. We did experiments that simulate an incremental melting process. So what we do is we analyze the composition of the melt in our experiments just at the time that plagioclase disappears from the mineral assemblage, so that's 15.5 weight% of melting. And then we kind of subtract that from the starting composition, the chondritic composition, so that we create a melting residue as a new starting composition. So we melt something that has already lost a liquid. And so when we do that, the major effect is that as we keep increasing the temperature after we removed the melt productivity decreases drastically because we remove a lot of the incompatible elements. So that's what this figure is showing. This is aggregate melt fraction as a function of the temperature for a batch melting process. And you see that after extraction of the melt, we only really produce just a few % of melt in the residue. And the effect of this is that we can keep pigeonite. So I'm now showing the composition of the pyroxene, the wollastonite content, so the calcium content of the pyroxene, as a function of temperature in both batch and incremental melting experiments, and everything with more than 5 wollastonite content is a pigeonite. So this is a trajectory for batch melting, where we lose pigeonite at 1200 Celsius degrees, but with incremental melting, because we just slow down the melting process, if you want, we are able to keep pigeonite at higher temperature. So a way then to distinguish between those two processes for Eurolites would be to be able to tell exactly at what temperature Eurolites form. So we need a precise thermometer to do that. And the thermometer that we found is based on the partitioning of chromium in olivine and low calcium pyroxene. So this is simply the amount of chromium in olivine divided by the amount of chromium in the low calcium pyroxene, and we could find a very clear correlation between this and the experimental temperatures. Then that is also independent of the exact composition of the plagioclase and of the oxygen fugacity, at least in the range that we investigated. So we can then use this simple relationship to calculate the temperature at which Eurolites equilibrated. And that's applicable to all Eurolites, as long as they contain one low calcium pyroxene, OPX, pigeonite, and an olivine. And so this is here the total population of Eurolites for which we can apply the thermometer. And so we notice that there's a wide range of temperature over which pigeonite was stable in Eurolites. And that's include relatively high temperature up to, let's say, 1260 Celsius degrees. And so, yeah, that is consistent with incremental melting, okay? Because batch melting, pigeonite disappears at 1200 Celsius degrees. So in order to keep pigeonite up to those higher temperatures, you can only do that if you have removed the melt progressively. So that's, yeah, one argument. Another argument in favor of incremental melting in the uralite parent body is the based on the calculated calcium concentration in the melts that were in equilibrium with uralites. So that's again parameterized based on the experiments, and yeah, using the Pachon coefficient, we can then calculate for all of those different uralites what would have been the concentration of calcium in the melt that was produced. And so we see that the trajectory is significantly different from the batch melting experiments, regardless of the exact composition. And this increase in calcium concentration is actually consistent with incremental melting. So this is a P-melt simulation for CI Achondrite, and that really shows clearly the difference between batch and incremental melting. So yeah, overall, again, the urite parent body is consistent with having been first rich in alkalis and only became depleted in alkalis following incremental melting. And so this melt that is rich in calcium, we also have traces of it in among uralites as kind of anomalous low temperature uralites that plot here under this line that represents the stability of pigeonite from Cycling Orzo 94. And so those contain augite, big crystals of augite that have weird, polychoetic textures and consistent with having formed from calcium-rich melt. So from all of those, we can kind of draw a little schematic for how we envision the uralite parent body. And we have melting residues that are quite different in composition, probably just results from initial heterogeneity in the kinetic material. With different, representing different FO2 conditions. Because they were equilibrated at the same temperature, we assume that they form at the same depths. And then those other samples that are more rich in calcium could represent some type of cumulates, or at least crystallization products of some type in the outer shell of the parent body. But in any case, melting seemed to have been incremental, and that would also explain why we have such a wide range of oxygen isotopes that plot on a mass-independent fractionation trend in uralite. So for differentiated meteorites like the eucrites from Vesta and Martian meteorites, usually the rocks plot on a mass-dependent fractionation trend, but that's not the case for uralite. And in order to maintain this heterogeneity, well, it's easier if you never form a magma ocean, but you just keep moving the melt as you form it. Okay, so I'll just summarize everything that I said. First, we need high NAK number planetesimals to produce the melts that are rich in silica, aluminum, and alkalis, and that those melts were mobilized in at least 5 parent bodies. So something that was like an LL-like parent body, the Brackenite parent body, Acapulco Ladronite, uralite, and the parent body of EC002. So all of those had all of those parent bodies come from the inner solar system, and they have a high initial NAK number, So that suggests that the alkali depletion and possibly the depletion in other volatiles is a secondary process that is due to volatilization, possibly in magma oceans like for Vesta. So we do have both evidence for batch melting, for example, EC002, which could be a 25% batch melt just extracted all at once. But we also have evidence for incremental melting with progressive extraction of the melts during melting, like in the Eurolite parent body. Then there are a number of questions that arise from this, and that's something I would be more than happy to discuss with you. So we have a very high viscosity at the beginning of the melting process, and that could cause sluggish melt extraction in some parent body, like the parent body of EC002, and potentially then also lead to retaining the heat source, which I guess I did not mention, but is aluminium-26. So if we retain the heat source, we can also keep increasing the temperature and melting further to form magma oceans like on Vesta. So yeah, what's the role of the viscosity in this process, and under which circumstances can those low degree melts be extracted? So despite the high apparent viscosity, like for the Eurolite parent body. So there are several possibilities, and one of them could be that the melt extraction is driven by a fluid phase, or that some these volatiles lower the melt viscosity enough to mobilize the melt. So there could be some smelting, which is production of CO by reduction of the silicate with graphite. And then recently, I recently heard about this study by Han and Bose, where they found a significant amount of water in Eurolites, despite the fact that there seem to be residual mantles. So that could mean that there was even more water before they started to melt. And that could, of course, then drive the melt extraction. Yeah, and so one last question. We have planetesimals that formed magma oceans, other that did not. Why is that? Is it purely based on the time of accretion and therefore the initial aluminium-26 that they contain, or is it really, or could it be instead the efficiency of the melt extraction and whether or not we retain aluminium in the interior of those bodies? Okay, that's all I have. Thank you very much.
Thanks, Max, for the really interesting talk. Do you, any of you guys have questions? You can just write in the chat, or you can just raise your hand and I can just unmute you. And Raj, go ahead.
Yeah, great talk, Max. I was wondering one thing. In some of your slides, I saw you had some information related to the oxygen fugacity of I believe, the Eurolite parent bodies and so on. That from your experiments directly, are you constraining the oxygen fugacity, and are they based on the, let's say, the phosphorate content of olivines, or are you taking those oxygen fugacity from independent like literature estimates?
Yes, so we calculated several ways. The way we first calculated is just based kind of on the position of the CCO buffer at those pressure and temperature conditions. And so we assume that we are on the CCO buffer, and then we calculate the position relative to the iron rustite buffer. So yeah, that's based on literature, and that gives us kind of the target FO2. Then another way is to look at the concentration of firelight in olivine, and yeah, assuming that it's in equilibrium with metallic iron, and that also gives us an estimate of the FO2, and the two match very well. So yeah, we are pretty confident that we can control the FO2 just using the CCO buffer to be between -1 and -2.5, and that's why we have such a also wide range of olivine compositions in our experiments that represent the full range. So we have olivine forsterite 65 to 90. Oh yeah.
Thanks.
Maxime, go ahead.
Yeah, thank you for the very nice talk. So my question was about the extraction of melts. You mentioned the high viscosity of the melt, which I can totally understand affects the percolation. I was wondering if the size of the parent body might also play a role in the sense that if it's too small, then probably the gravity won't be efficient enough for buoyancy to be significant. Is that something that has been looked into?
No, you're right, absolutely. So usually we assume that, I mean, I did those experiments at low pressure, so of course I will assume that the parent bodies are small, like between, yeah, just let's say around 200 kilometers in diameter or less. Well, or in radius, I don't remember. But that's also, yeah, having a larger body would help to mobilize those melts as well, of course. Yeah.
Okay, thanks.
Okay. So I think Andrea, you have a question you can ask.
Yes. Hi, Max. Thank you very much for the nice talk. First of all, I'm not a planetary scientist or geophysicist, so my question might be not particularly relevant. But you know, one of your question is why some planetesimal do not reach the magma ocean phase. So you know, from purely the analysis of meteorites, I mean, can you tell how? So what is the fraction? So how rare or how common are these? Based on your analysis, this planetesim might not reach magma ocean. Are we talking about, you know, a tiny fraction, or we just don't know?
No, it's a great question. Yeah. So how many? So there are at least 5. So that seems like not that many, but if we put on the other side the parent bodies that we clearly know had magma oceans, maybe that's Vesta and maybe the Angrite parent body. So maybe we have 2, so it's 5 to 2. Then there are also a lot of other meteorites that are ungrouped that have various concentration of alkalis, but the question is always, do we really need a magma ocean to get rocks with low alkali concentrations? And so of course one thing to do would be to compare the alkalis against another incompatible element that is not volatile, or get some isotopic composition of the potassium. And so this work is also being done by other people, and hopefully that will give us a better picture of exactly how many bodies were affected by the magma oceans and how many were not. To me, it's not obvious that the ones that did not see magma oceans are lower in number. I would say it's at least comparable.
And can I ask a follow-up question on them?
Of course.
So for this object where you don't need a magma ocean, and this is really probably a crazy question, but I mean, do you need a parent body at all? I mean, do you need this to happen at high pressure, or say you have some small planetesimal in the early solar nebula that experience high temperature just because it's embedded in a radiation field that is hot, and it gets partially melted, but it's not inside any larger planetesimal. I mean, would that work as well?
Yeah, it's a bit harder for me to reply to that because I'm less familiar with those type of processes. And
do you need the high pressure for this to happen, or?
No, the high pressure, not necessarily, no, because yeah, I mean, even my experiments are just well, you need the high pressure. Okay. One thing I guess I could say is that you do need the high pressure. For example, the Eucrites that I talked a lot about, they contain graphite, and so you can put a minimum pressure constraint on the fact that you have graphite in equilibrium with an olivine that contains iron, because at very low pressure, graphite is very reducing, and so you would so for those at least, and for many parent bodies that do have kind of iron in the silicates in equilibrium with graphite, you need a body that is at least 100 kilometer in diameter. So yeah, okay, that's the most immediate way I can see to answer that. But yeah, it's interesting.
Max, can I ask you a question? So can you move to the slide that showed the CC and C dichotomy, that chromium versus oxygen isotopes?
How can I leave the? Okay. Yes.
Yeah. Okay. So I think something really interesting in this over here is like when you see this NC meteorites, like the ones in the inner solar system, you see a higher initial bulk sodium potassium number, and for the outer solar system stuff, you see lower numbers. So so basically what we believe is this is something related to the water line, so for example, outer solar system meteorites formed beyond the snow line, and they created water, and then due to aqueous alteration you can remove a lot of sodium and potassium from them. And while if the inner solar system body is accreted within the snow line, you won't be accreting a lot of water. So basically before melting you have aqueous alteration. So aqueous alteration wouldn't play a role in depleting them in sodium and potassium with respect to the primitive compositions. And for the outer solar system meteorites, maybe water did play a role and took out sodium and potassium before the melting could take place. Would it be possible?
That's an interesting thought. I have not considered that. I think that the pattern, so at least for the carbonaceous chondrites that have been well characterized, like CVs and CMs, and that we know are depleted in volatiles and rich in refractory, the depletion pattern is pretty smooth, and it's not just like fluid mobile elements that are affected. So for those, I think it is really kind of a primitive composition before both partial melting and any type of hydrothermal alteration. But yeah.
But I think for a lot of CVs and CMs, I think we see they are severely aqueously altered as well. So there are very few like primitive ones.
No, so I would expect that they contain more water, but I don't think that it explains the depletion in moderately volatile element relative to calcium, and that they're kind of two different characteristic of those rocks. But yeah, I don't know why all of those are. There are some theories around that I'm not super familiar with them, about how Jupiter create a pressure bump in which CIs can accumulate, and maybe that explained the overabundance of calcium. But I'm not sure if it really explains the whole pattern of depletion seen in carbonaceous chondrites. So I don't know. So yes, sea ice, they are, like the sun's photosphere, and they look in terms of NAK number the same as a lot of the inner solar system material, but we suspect that sea ice, they come from even further away, right? Really out there, and those were full of water too. So yeah, I'm not so sure of what to make in kind of the CC part of the diagram.
And do you did you consider the role of water in the melting, like the experiments that you did, and then the inferences that you based on, like say for example, like a uralite parent body had more like an incremental melting? Do you think, like based on the accretion zones, that could water accretion of ice and introduction of water in melting, could that play a role in the viscosities and from the degree of extraction of these melts and all that? Can it?
Yeah, I know. I think it should. And of course, my experiments are anhydrous. So yes, that would definitely, if it is confirmed that uralites still contain thousands ppms of water despite melting by 20%, then yeah, it could indicate that the produced melts initially that were water rich, and so in order to characterize those melts, one would need to make new experiments, that contain water. But I think it should, of course, help with melt extraction then. Yeah.
All right. Do any of you guys have any more questions? Okay, it seems so. All right, let's thank Max once again for the really interesting talk, and we'll see you all again next couple of weeks later on 21st of September by talks by Anders Johansson, who is basically an astrophysicist. So basically we'll be switching gears and talking more about the astrophysics part on 21st of September, same time, 12 p.m. Central Time. So yeah, I'll see you guys for there.
Thank you.
Thanks Max again.
Bye. Thanks, Max.